Okay, let's talk about heap sort. Heap sort is an in-place sorting algorithm. It don't use actual space. We first sort the array into heap order. Then we repeatedly call the delete maximum in order to further sort the heap into increasing order. The first thing we do is we try to reindex the heap, reindex the array. We start from index 1 instead of index 0. The reason is we want to calculate the parent index and the child index. The parent index is current index divided by 2. The left child is the current index multiplied 2. And the current index multiplied 2 plus 1, we get the right child. If we start from index 0, this formula won't work. However, the array is start from index 0. When we access the array, we need to minus 1 from this index. Okay, it will become apparent once we walk through the algorithm. First, we start from the last index until the first index. We call this sync in order to restore the heap order. If any parent is bigger than its two children, the heap order is established. If that's not the case, we exchange the bigger child with the parent in order to restore the heap order. So let's start from index 7. Index 7 have two children at position 14 and 15. They are not in the array, so we don't have to worry about it. Index 6 again don't have any children in the array. 5 don't have any. 4 don't have any. 3 have children at 6 and 7. So we see the bigger of the two children is 8. 8 is bigger than 4. That violated the heap order, so we exchange them 8 and 4. Next, we go to index 2. Index 2 have two children at 4 and 5. The bigger of them is 6. 6 is larger than 2. This violated the heap order, so let's fix it by exchanging them. At index 5, there's no longer have children in this array. We are done. So let's go to the next index, which is 1. 1 have two children at 2 and 3. The bigger of them is 8. 8 is bigger than 3. This violated heap order, so let's exchange it. Now at index 3, the two children is at 6 and 7. The bigger one of them is 4. 4 is bigger than 3. This violated the heap order, so let's exchange it. Now we are done. This is a heap. At any node, the child is smaller than its parent, so we can now call the delete maximum in order to sort this array. In order to call the delete maximum, we first exchange the last element with the root and put the last element outside of the heap. Now, this root element violated the heap order because the two children are at index 2 and 3. The bigger one of them is 6. 6 is bigger than 0. This violated heap order. So we need to exchange. At index 2, the two children are at index 4 and 5. The bigger of them is 2. 2 is bigger than 0. This violated the heap order, so we need to exchange. And there's no further exchange needed. We restore the heap order. We can call the delete maximum again on this heap. So let's just do that. We exchange the last element with the root and put the root outside of the heap. And this violated heap order because the bigger one of the two children is larger than 3. We need to exchange it. At index 3, there is no more children in this heap. Then we just restore the heap so that we can call the delete maximum. We exchange the last element with the root, then put the last element outside of the heap. And we sync it down. The 3 is bigger than 0, so we exchange the root with the bigger children. And we just restore the heap. Then we coordinate maximum again. We exchange 1 with 3 and put 3 outside of the heap. And we sync it down. The bigger children is 2, so let's change 2 with the root. And we just restore the heap order. And let's call this again. We exchange the last element with the root. Put the last element outside of the heap. And we sync the root down to the right position. So we put 1 here, put 0 here. We just restore the heap order so that we can coordinate the maximum in the next iteration. We exchange the root with the last element, put the last element outside of the heap. And we call sync, but there's nothing to sync. We only have 1 element, then we are done. This is a increasing order. Let's calculate the cost of this algorithm. In order to build this heap, we start from the last element to the first element. Each time we call sync. So the cost for that step is n multiply log n. And again, when we call the delete maximum, we iterate through the last element to the first element. And every time we call the delete maximum, the cost is log n. So again, we get n multiply log n cost. So the total cost is proportional to n multiply log n. This is a big O for this algorithm. And the space cost is 1 because we didn't use any auxiliary array. Everything is doing in place. So now let's write a program. Okay, this is a normal exchange function. However, our index starts from 1 instead of 0. Here, in order to access array, we need to minus 1 because our array index starts from 0 instead of 1. This is a little bit different. Now we need to restore the heap order. This is a normal way of doing that in the section of the priority queue. Let's write it, then we talk about the tweaks. Okay. the first thing is we calculate the index of the left child. If the left child is not at the last index and the right child is bigger, we want to get the index of the right child. If the heap order is not violated, then we break. Otherwise, we exchange the parent with the bigger of the two children. Finally, we increase the index for the next iteration. However, our index starts from 1, so whenever we access the array, we want to minus 1. Here again, we want to minus 1. When we access the array, now we are done. We are able to restore the heap order. Now we can write the sorting algorithm. Static int. Okay, sort. In this case, we return A. However, with our for loop, we start from n divided by 2 instead of n, because we know for sure those index won't give us anything because their children is not in the array. So we start from n divided by 2, which is index 3 in this case. And I above equal 1, I minus minus. Oh, we haven't calculated the n yet. The n is the array size. For this, we repeatedly call a I n. Then we just establish the heap order. Once we have the heap, we can repeatedly call that they need a maximum. We first exchange the root with lost element, and we put them outside of the heap. Now we call the sync A1n to restore the heap order so that we can call it again in the next iteration. Now we are done. So let's prove this is working. Okay, as you see, it sorted the random array into increasing order. This is a heap sort with cost NlogN and space cost 1.